Hello and welcome back to Compiled Programming. Today is going to be another one of the non-coding episodes, and I did a few comments in the last few videos about we're going to use data structure X, or we're not going to use arrays, or we're going to use blah, and I thought it would be a good idea to actually have a quick tour of what data structure we're using right now, and what we're going to be using, why, and what's all that about. So we're going to start very obviously with the fact that we have some memory in the computer, and memory basically goes from address 0 towards some kind of address X, and we have a bunch of bytes in between for that memory. And since a memory is just a gigantic array or gigantic lists, then this is the most natural data structure that we can do, and this is what we have been using so far. This is, in general, should be a default for everything, more or less. One of the examples of what we use it so far for is buffers, right? So we ask for the buffers for our code, and we ask for buffers for our data, and we have this temp allocator, which is basically just we ask, okay, till here is going to be on our big buffer, which we consider temporary area, and every time we just slice a piece more of it, and a piece more of it, and a piece more of it, and until we are done. So obviously there is this question that if you do multiple allocations, so let me grab another color just so I have something else. So say it was allocation 1, and now here I did another piece of allocation like so. And if I want to now go back and I've filled in this stuff, I need to do something about it, right? I need to, if I want more, I will need to go over here and get a bigger piece. And this is a question about resizability and general memory usage, memory fragmentations, and so on. In general, if you know how much memory you need, and this amount of memory is not dependent on the input to your task, or you have some artificial limits on the input of your task, then having fixed size buffers is the simplest options, because it usually will yield the best performance. It means that your program is very stable, it has known complexities, it has known memory sizes. It's just simple to say, like, I don't know, I want to have 2048 entries, or we have maximum 2048 functions in that we're going to compile or something. Obviously, it's an arbitrary limit, right? We just decide that this is enough for everyone or whatever, and we're just going to limit the size of our code to be this number. Now, obviously, at some point, someone will write a program that will need 2049 functions or 2050 functions or whatever. And this is where there is this question, right? Okay, maybe I should always just be using something that can grow in size, right? Something that is that can support this arbitrary number that comes afterwards. Okay, so what can we do about resizable? Well, the simplest form is resizable arrays, or they're called vectors in C++, right? Where you can say, oh, I just want to have some kind of storage for my, I don't know, type int. And I don't know how big it is, right? So unlike here where we say this is, I don't know, int 248, I just have something, and it's set in C++. This would be like a vector int. In C, you don't really have anything to deal with resizable arrays. You have to do it yourself. There are some nicer libraries, there are some not nicer libraries. Usually people who write in C end up adopting one of them or writing their own for their own preferences. I have my own stuff, but this is sort of very C specific why it's a problem. So I'm not going to touch too much on that, but because the basic idea is the same no matter which language you're using. It's just the fact of, okay, I don't know what goes into here, like I don't know this number. So I just want to fit how many there are. The thing about vectors or resizable arrays or whatever you want to call it is it is unlikely that this is what you want. And some people may throw stones at me for saying that, but let's just look at this. So you can have several situations for what goes in here, right? You can have very small things. So let's say that you have, I don't know, you have function parameters. And the majority of the functions, like vast majority, would, for example, be between 0 and, let's say, 3 parameters, or, I don't know, 7 parameters. Doesn't matter, right? Majority of the functions will have very few parameters. So you would have, first of all, the overhead of this data structure will be quite big. Because vector needs to maintain at least its current length, capacity, and the pointer to actual memory. So there will be at least, I don't know, 24 bytes for extra for this. In some cases, depending on the implementation, it will be much more than that. So you would store like, I don't know, 0 pointers, and you would waste 24 bytes of memory on storing 0 pointers. Secondly, you are making majority of the code more complicated. And thirdly, you make stuff slow, because also usually, especially in C++, you would have a situation where what you store here are not actual objects. They're going to be like pointers here for several reasons. And that means that you have like several hops. If you say I have like I have a function object, and as I said, it has like args, which is a vector, right? Which is a vector, whatever. Then you have a this is stored by value in the function, but then vector itself points to some memory, and very likely these things here, as I said, are also pointers. So you have something like another piece of memory, and if this piece of memory is also allocated using malloc or new in C++, doesn't matter, right? Malloc, new, they both do the same thing under the hood. Then you just have these 3 levels of indirection here, and all of that to represent several items most of the time. And more than that, it's also like quite complicated. So what would you do instead here, right? Say, okay, you say that that's bad, what would be good? Well, the thing about data structures in general is that most of the time, if you want the best performance, if you want the best like memory consumption, or the little memory consumption as you can get, you have to do something slightly custom and slightly weird. And this is again where, for example, C is pretty terrible at that. C++ is slightly better, but not much. Having a lot of control and a lot of, at the same time, security about memory is very hard. But what I would do here if I wanted to write something like more robust, not something that we are writing in the current series where we are just trying to get through functionality and trying to make things work, then I would do it like this. So first of all, when you trying something to make it work, then vectors are perfect. Like if you're doing C++ and you just need to do something like this, function has arguments, sure, go for vectors, makes total sense. It is pretty straightforward. But later on, you might figure out that it might not be the best way to do this. For one, when you're dealing with data structures, you have to figure out ownership, and not necessarily in a sense of like pointer ownership with modern C++ or stuff like this where you have smart pointers, but in general, what belongs to what. In the case that I have here where the function has arguments, it is literally that, right? A function has arguments. Like you can't have arguments separately from the function. They don't make any sense. So probably you would want to make a standard case very fast and have the side case, well, maybe a bit slower, but it's okay because it is side case, right? So if you're writing a real language and you're like, you have a purpose of programs and you have, I don't know, say roughly 1 million lines of code of this new language, and you're like, okay, now I want to optimize my memory usage and I want to optimize whatever speed, for example, with where this compiles in. Profiler will not necessarily give you anything useful here. It will not even necessarily show that you're spending a lot of time in vectors because you may end up just paying that cost spread so much across your program that it's not necessarily going to be visible. Of course, some profilers might be more useful here while others don't, but abstracting from that, you could look at this stuff and say, okay, I have a lot of programs here. I know that I can go through this input and figure out this number, because this is what we are interested in essentially, right? You want to know what is the majority case for your program. And you say that, okay, majority of the case, I have like on average 3.4 arguments per function. Okay, so I will have inside of my function, maybe I will reserve space for arguments. So I will have, sorry, an eraser. Yeah. I'll just have this arg and then 4 or something, and they're just going to be part of this object. And this is going to be what you can access right away. These are going to be stored there by value, and you're going to be able to access them very fast next to any other information that you have about the function. Obviously, you don't want to make the function object very big, but something like this might make sense. And if you have more than that, then you would have an extra thing saying, okay, those are extra arguments. Maybe not. Maybe that having them separately is also makes sense in different cases. And this is also something that you need to figure out. And you might hear terms something like data-oriented design and whatever. The basic idea is you, besides knowing a lot about your input, so when you deal with this stuff, you again need to know about your input. So you need to be able to understand what are you trying to represent and what is statistically more probable in the stuff that you're trying to represent. But also you want to understand what you're doing with what is represented. For example, again, coming back to our arguments. Well, in which cases do we care about arguments? And do we care about them separately from the functions, right? Are there passes in the compiler that deal exclusively with arguments? Well, not really, no. Because arguments, we want to know them whenever we do type checking, like are the arguments that we are passing to the function matching the arguments that we are expecting in the function, or when we are trying to resolve overloads, we say, okay, these are our arguments, which function actually matches matches them, right? So maybe like you have type checking, you have overloads over here. So there isn't really a situation where this stuff is not connected to a function. So more likely that you will need to get this function object regardless of whether you are doing something to arguments. And in this case, it probably makes sense to store them together. And this is why I said that like we probably don't want them separately, because they are not processed separately as well inside of our program. As an example of what can be processed separately, well, I guess what we were dealing with the past few episodes is imports. And you also notice that they are kind of just their own thing that is pointed to from our main program. Because imports, unlike, for example, arguments, we have multiple passes that deal with them. So in P32 executable generation, we need to go through them something like 4 times, and we're just going end to end through all the imports, right? We are just doing passes over passes over passes of the imports. So it would be great if imports were also done in such a way that makes it easy to make those passes. And right now they're not necessarily fully that, because they are like these nested arrays and whatever, but it's still worth just paying attention to how your data is being processed. Are you like, what is being processed together and what is being processed separately, and then thinking about that. So let's just have some bullet list for what to think about when you're choosing a data structure and choosing a memory layout. So first of all is does it depend on input in size? So this is a very first question that you should ask yourself and try to understand. Like, is this some constant that is always the same, or is it something that can be made constant? If so, just make it constant and forget about it. Also, this comes up a lot in cases like caches, because usually you say, okay, my cache is size n, and whatever doesn't fit into cache is just evicted. But it's something that you should think about before you choose how to represent data. The second point is frequency in input or structure of input. This is also important because if you look at data structures like vector or whatever that is in standard library in C++ or other standard library, they are usually designed around being very agnostic of what you're doing with them. So we just, okay, it doesn't matter how you access the stuff, just you're gonna throw something in there. I don't care about what is the size of my item. I don't care about anything. And that means that they're making certain trade-offs about how they implement it internally. If you want to be thorough about this, you definitely need to understand your input. Again, in case of compiler, another example would be, I don't know, ID sizes. So yes, there might be some obscure weird program where usually the size of your identifier is going to be 2 pages of text, but majority cases they are going to be quite smaller than that. So maybe you can take advantage of that and do something clever there. Is it worth it? It's obviously you need to profile it, but at least thinking about that and thinking about what are the averages and what are the outliers in your import is quite important for this type of design. Okay. What else do we have? Yeah, so the third thing is, as I mentioned, how is data processed? Or maybe better name for it would be which data is processed together. And this is what I showed here, right? You don't process usually in the compilers arguments separately from the functions, but you totally process imports for all of the functions in one batch, or all of the output data or whatever, right? Do you have such passes that just go through uniform list of stuff, and you need to make those passes fast? So this is this is something to think about. And this is, again, there is this whole topic that I don't want to go too much into, because there are very polar opinions about it. But if you want to look into this, I think it's data-oriented design or something like this. But yeah, you can look into this stuff on your own if you want. Okay. These are kind of very high-level things, high-level questions to ask yourself. And this is something usually that is not part of the more traditional choice of data structures. So if we are talking about more traditional things, then the next thing is kind of a side effect of which data is processed together, but you also have this thing about access patterns, right? Do you access data randomly? Do you access it sequentially? Or what is your choice here? Or also, so let's just have these side ones here. So random versus sequential. And here you can also have frequency. And the frequency one is kind of interesting because depending on what you're doing and the magnitude of frequency, there are some choices. Usually frequency comes up together with caches. So if there is a big chunk of data that you generally need to know about, but only some portion of it is needs to be accessed fast, then the cache is your choice, and other stuff is not important. So you definitely need to understand like how frequent something is. If you want an example of that, let's say that, again, since we are writing a compiler, a good example would be plus operator versus, I don't know, obscure intrinsic. So let's say there is some kind of obscure instruction for your RISC-V CPU that nobody right now uses or whatever, and you have a function that deals specifically with that instruction, and you have another function in your code that is plus. Well, it's pretty obvious that a lot of programs will have plus, or even more programs will have like assignment or something. So if you have this gigantic list of identifiers, well, you can just shove all of them into one giant hash map, and maybe that's gonna give you a best performance. Or maybe you can think about it and say, actually, like there is a hot set of things that need to be accessed like really, really fast, and then there is not so hot one that is just not gonna be that, and something you can keep with, I don't know, less collisions in hash, something you can keep otherwise, or something you even upload to disk, right? You never load this stuff by default. It is lazy, and you only load it when necessary or something like this. It's not necessarily something that you should be doing, but again, just thinking about it, is your data uniform? Is all of your data accessed in exactly the same frequency and the same amount or not? This is something that is really important, something we should be thinking about. Getting back, for example, to this stuff, all the imports are accessed in exactly the same amount, at least in these passes. Like we're always going to go through them multiple times when you're generating executable, and there is no like more frequent or less frequent in this case. But there is frequency definitely in the case of identifiers and looking up which functions we are using. So maybe it's worth doing something there, maybe not. Again, you need to measure and figure out. Okay. Getting back to this stuff is random versus sequential. This is a standard thing that you can read in any computer science books, where they say, okay, you have sequential access, you go for arrays or vectors or whatever you want to call it, and you just use that. If you have random access, you probably want something like a hash map or something like this. And I will go and explain how those roughly work a bit later. But before that, I want to maybe add one more thing. And this is more important when you're talking about languages that deal with memory directly, namely like, I don't know, C, C++, D, Rust, whatever. And this is stability of pointers. And this is something that actually triggered this episode and something I mentioned multiple times. And it has to do with the resizable arrays. So again, we had some array. Let's say we had this, again, we had the function, and this is our args array. We realized that by default, we usually don't have more than 4 elements. So we have this 0, 1, 2, 3 indexes there, right? So when we created this array, by default, we created it as a size of 4. Great. Now we have a gigantic function from Windows API that has 12 parameters because they can. And you need to push this 4th element. Well, if you call realloc, which is what is typically used for this resizable array, then one of two things actually going to happen. If you're lucky, realloc will realize that the memory over here is actually not taken, so nobody yet took this, and this would happen more frequently, I guess, if you have not done anything that did allocation in between you allocating this array and you are trying to resize it. So I think they even optimize for this case where you like create an array and then you just constantly push stuff into it. This will probably be a good case, and you get just more memory here. You'll suddenly realize that, oh, actually I can use more stuff here, and it's great. However, since you cannot rely on this case, there is this other case that you need to be aware of, where instead of that, you would get completely new memory set over here that has nothing with previous one. Realloc will copy this stuff here, these first elements, right? It will copy them, so everything is going to be great. But for example, this was at address 0x, I don't know, 10, and this is going to be at 0x 74, and of course like 74 million or whatever. The point is, if you had a pointer to this thing, so you had, let me grab a different color. So you had a pointer saved to this argument, and you had it saved somewhere. It's like you have a variable called my favorite argument or whatever. And this is a pointer to here. Once you have resized the array, this pointer now is pointing to bullshit memory. In C++, you can have, you can do things to mitigate this stuff. They all cost you some CPU. They are all not very nice. And in general, this is why I mentioned that when you have these arrays, it is quite common to put pointers in them, because if you copy a pointer, so if here you had a pointer instead of an actual object and you copy it here, then everything is fine. You're always, both the pointer is valid because it was pointing to some memory over here. That was the actual object, so my arg. and you copy the pointer over here, and both this guy is happy because it points here, this guy is happy that it points there, and between copying everything is fine. The only cost of that, of course, is that if you do these kind of allocations separately, then you're no longer accessing memory sequentially. So like you lose a lot of the benefits that are coming with the CPU prefetching, because when you have a loop and it just goes through all of these elements, and CPU realizes that you're just literally going through the memory forward or backward, like the CPU prefetching is kind of complicated now, but definitely forward and backward they understand very well. So they can, while you're processing this one, they can realize that, okay, you're going to be actually over here next, and then over here and over here. So they will just push this stuff into cache and generally make your program not wait for memory. If you suddenly have your argument over here, and then this argument can literally be over here, it's a completely different address, you're starting to pay for this. So I try to avoid this stuff and try to make sure that if I'm using arrays, they are stored by value. But again, this causes this kind of problem where you can no longer take a pointer to this object, because if array is going to be resized, you're out of luck, right? You just have a pointer to some memory that was already not yours and doesn't have that object, because realloc will just kill this memory. And you're going to be very sad when that happens. So what can you do about this? There are a couple of things that you can do. Thing number one is to not store pointers, because what you could do is have just my favorite arg index and my favorite function. So you introduce some other way to find this element. So some other address in your system that would uniquely identify this stuff here. Now, this doesn't always work. Especially it doesn't always work when you have when you need to access this stuff fast. So if this is something that you need to find at some point somewhere for whatever reason, this might be okay. And in general, this works. Also, it works if you need to do this stuff really, really a lot and you can't really do anything about it. You have to have flat buffers, and like this is the only way your program can be structured. Then this is okay, this works. Specifically in C, it has a big issue that you can't really attach any kind of type information to this, because this index is literally just going to be int, right? It's just going to be some number somewhere that has no type attached to it. It means that you don't know that this index is actually indexed for this very specific array, and you can accidentally use it for whatever else array that you want. So it has these safety problems, but you can do that. And actually also I believe in games you often would have these, so you have these gigantic lists of entities in the system, and then you would have entities talking to each other through entity IDs. So you'd have an ID, and then you would look up this ID in these lists. So some other way to address this array. And again, this works. It has these problems of time safety and sometimes problems with speed, but in general, it's not too bad. Another way how you can deal with it, which is changing now data structure to a different thing, is with something called, I'm actually not sure what the official title it is, but let's say we call them bucket arrays. Bucket array. And the idea here is that you never reallocate memory. This is not always as efficient as a traditional array, and you'll see why, but it has this benefit that you can take stable pointers to that. And this again comes towards this discussion. So stability of pointers should be a consideration for you. And the idea of bucket array is that, okay, you had these 4 elements, and this is what you allocated right away when you created an array. These are your 4 stuff, so 0, 1, 2, 3. And then now you're like, oh, I want to have a 4th one. Well, what usually happens is there are various options how you can do that. You can either have a linked list, so you can have, say that at the very end of this, and let me grab different color maybe so it's more visible. So at the end you would have like a pointer to a next block, and the next block can be the same size, which usually is nicer, or can be different size. But then you just say, okay, I have this new chunk of memory, and this new chunk of memory is just the same as the other one, and the indexes continue. So this is going to be 4, 5, 6, and 7, right? And the benefit here is that you can store these things. Here you can store the argument by value. It doesn't have to be a pointer. It can be actual information about argument. You can have your favorite argument pointing to this, and everything is great. This memory is not going to go anywhere until the end of the program. If you Again, depending on your access patterns, you might not want a linked list here. So if you have to often have indexed access, so if you often need to know, for example, what is the 6th element, then in order to do that, you would have to like go to this bucket, realize, okay, this is actually the next bucket, go to the next bucket, which is very inefficient. So if you want to maintain this kind of setup where you have constant memory access, then you need to not use linked list here, but instead your bucket array will itself just have, basically you turn it into a 2-dimensional array, and this top one is just pointing to these ones, and this is the standard array, standard resizable array as we did here. So this one is getting reallocated, but because you are never taking a pointer to the bucket, you don't care that this stuff is being reallocated whenever this grows, but these guys are stable in memory. They don't move anywhere. And even in terms of caching, it's not necessarily that bad, because like cache is given to the CPU like in blocks, and those blocks have sizes, so it's usually okay, but the access pattern is not always straightforward, so there is absolutely no guarantee that CPU will recognize this access pattern where you have double interaction, you have nested arrays. It might not, you never know, so this is something you definitely need to profile and understand. But in general, I think that bucket arrays are in general good options for cases where you need to keep pointers. And in the cases of compilers, you usually do need to keep pointers, or you need to have this stuff. Either way, because there is a lot of situations where you need to go back and patch in more information about some stuff, because you only recognize it later in the life of this thing. In the case of function, right, you first see a function and that function is not overloaded, and suddenly it becomes overloaded, so you need to somehow group it into bucket, or then you need to figure out where this function is going to be laid out in memory, like what is going to be the address of it, and there is mutual recursion. So there are just a lot of cases where you need to go back and change something somewhere, and having these stable pointers just makes it a little bit easier, although there could be other ways. You can always avoid, by the way, this whole problem of patching and whatever by just copying memory always, but that's a different conversation altogether. Okay, what else did I want to say? Well, I guess there is one side topic of bucket arrays that is important that once you go into this kind of setup where you have just chunks of memory that have some known one size, so I guess let's first talk about another data structure that obviously exists in probably 99% of the compilers, or 99.9, which is trees, right? So you have some kind of root, and then you have one child, you have another child, and you have more children here, right? So in majority of compilers, this is necessary because you have abstract syntax tree, which tells you about the structure of the program. You have plus operator, on the left it has A, on the right it has in parentheses B, or whatever, yeah, B calling of X or whatever. So to show you in more text what that looks like, I'm saying that you have A plus B of X. So something like this. You usually represent this program in the tree, so you can do various operations. And this compiler not necessarily saying that we will do it, maybe we will, maybe we will not. It's not important, but the topic is like tree is something that is quite common and something that you need to understand. But trees are also usually quite terrible at both memory, compactness, and cache coherence and whatever. So, be careful when you use them. Obviously, in some cases you can not use them. But if you do, you can also sometimes represent them in such a way that it's better for CPU to be dealing with, because what you can do is, again, look at these topics. And another one, I guess, that is necessary here is, let me remove this plus for now over here and just add one more stuff. And this is mutation patterns. Right? So how is your data mutated over times? And again, I guess these one. So if I get maybe something really bright. So these one, mutation patterns and random versus sequential reads and random versus sequential writes and general write stuff. So these are very standard computer science things that you can very easily learn in any book. And they'll tell you about this stuff, right? So in trees, usually it's very easy to replace this node, right? If you want to replace this node, I just need to change the pointer over here and maybe pointer up if the children actually point to their parent. If not, then not even that. So it's extremely cheap to do this operation. But on the other hand, you trade the fact that, for example, walk over tree, so going 0, 1, 2, 3, 4, we may access like, I don't know, 5 different pages in memory and be completely terrible in terms of cache. So this is something to think about. As I mentioned, you can do things. For example, if your tree, doesn't matter if it is AST or some other tree that you maintain in your program, if your tree doesn't actually change that much or change at all, then you can always just flatten it out in an array, right? You can say that, okay, we'll have this array here, and this is going to be my zeros element. Then I know that I can't do it, right? 0. This is my zeros element, and I know that I always have 2 children. So I will have pointers to 2 children. So, I will have, I'm pointing here, and there will be like a mini array in my memory saying, okay, this is 1, this is 2, and then 1 points, well, 1 doesn't have any children, so it doesn't point anywhere. 2 has children, so it's like it will point to this stuff. and they not necessarily go after each other. They can go somewhere here, but they still, depending on how you lay out and how you want to traverse the tree, you can create this flat structure that sort of represents array, but still allows you to very easily go through it and have decent performance in terms of cache. Okay. Yeah. Again, in C, both trees, bucket arrays, or even this kind of resizable arrays are all quite terrible to work with. So this is a bit unfortunate because there are no primitives for doing that, but we're gonna manage. That's fine. Obviously, one final one, very useful data structure that is everywhere is hash map. Let me grab another color. So we have hash map, and the idea there is that it's basically you taking this resizable array, but instead of just having some kind of index that you use to figure out which element to use, you take this index and you apply some kind of function to it that gives you another number. It gives you n, and or it gives you hash, right? So hash function, and hence the name hash map. And that function tells you where you should look for your thing. So say you want this this index doesn't necessarily have to be a number index. You can have a string, right? So this is very common, and this is would be very useful for us later when we do parsing, because if you have something like I don't know, again plus, or you have function foo in your program, you need to understand what is the definition of this function. So from this foo, you would want to get this function definition that we have somewhere. And they will be stored in hash map or something like this. But you want to be able very quickly to go from foo to the function. So there is some kind of processing of this string foo, that gives you number 7. It just says, when I see foo, I will give you 7. So let me add maybe another one here. So this is going to be our 7. So we say, okay, foo is located here. And that's great because now you essentially able to go from any index to a very specific point in memory with very little calculation, right? You don't need to go through the whole array and figure out, asking like, are you foo, are you foo, are you foo, or are you something else? So this is just the basic idea. You have some kind of key, some kind of, I don't know, usually it will be a string or a pointer, whatever, doesn't matter. You have a key and you have a value that is what you actually want to store there. So for example, here you would look up a function or identifier based on the name. Obviously you have the situation, the big situation here is that this is limited in size. So for example, this is 8 items because this is all we have. But if we want to push an item here and it doesn't fit, or we say that we have another identifier that is bar, and when we pass bar over this function, so let's just say that this function is, I don't know, we would have world's worst hash map, and the hashing function will be length. You would be like, oh, yo, it's really terrible, and especially if you know how hash maps work, like how do you even think that this is a good idea to have lengthed hash function? But let's say that we have it. Funnily enough, in PHP, I believe, in one of the first versions, this is exactly how hashing was implemented, which is great. But anyway, so say we say that we choose our index based on the length of the input. Okay, well, foo and bar both have the same length, and obviously I need to change this to 3 and this to 3, so they actually both point to here. Well, now we have a problem. We want to store function foo and function bar in the same location in memory. That doesn't work. So hash maps have different strategies how to deal with this stuff. You can like put another array over here that stores all of them. You can just put it in the next cell and try to verify this. But the point is, this main structure operates the same way as any other resizable array. You can never take pointers to stuff stored in hash maps because of this stuff. Like it will just do weird things with the stuff that you have. Like you can. I don't think there are even hash maps that support stable pointers because that will make them really, really inefficient. They always want to move things around. So yeah, this is something just to consider for pointers, for hash maps, sorry. And this is why when you're referring to something stored in a hash map, you always store the keys. So again, you can't store pointers to this. You would use a variation of this stuff, and namely, you would store the keys. So you'd say I'm calling function foo, and then you look up foo here, and this is what you use. The reason I brought this up is because there is actually a variation of the tree that, and this is kind of, there is a mutation of bucket array and trees that actually has some of the properties of the hash map. And if you want to learn one tree structure and like really something that you can use more or less universally, and it won't have terrible side effects in majority of programs, I would say learn B-tree, because B-tree is it's a mixture between a tree and a bucket array. You have array, but at each node you don't have one thing. Instead, you have multiple things, and the actual size of this stuff is really should be chosen very carefully based on experimentation and on the cache sizes in your architecture and other stuff. But it is some number. Let's say, I think in modern Intel processors you would have like 64-byte cache lanes. I think maybe somebody can verify that. But anyway, this is usually not too big but not too small size here, and then you build a tree out of this. So instead of just one child, you would have how many childs are fitting into here. So probably, I don't know, 8 children, right? Let's have these 8 children here, and they themselves have 8 children, and so on and so forth. And what's cool about this is, first of all, at the very edge where you actually store values, you still have essentially like a bucket array. So you still have quite a large chunk of values that is kind of nice. If you want to make them stable, you can actually do that, although that will make B-tree quite inefficient. But the thing about B-trees is that they're usually quite short. So what is called the height of the tree, I can maybe zoom out a bit. So how many nodes are between the root and the last node is called height of the tree. And B-trees, because they have a lot of elements in each single node, they don't have large height, because you have this sort of, the exponent goes, so your n goes into exponent, and usually you would have like 3 or 4, maybe 5 levels maximum. Like it's very shallow tree, and that means that the lookups in this tree are also really fast. So B-trees can work as hash maps, so you can also look up stuff in them. Unlike hash maps, yes, it's not a single lookup, so you usually would have to go through several steps to get to where you're going. So the values are traditionally stored over here and not in these nodes. So there are B- trees and B+ trees. You can look into both of those versions. So there is b minus tree and b plus tree. The only difference is, are you storing things in here or are you also storing things in here? But these are details that you will need to look into if you want to implement something like this. As a general idea, I'm trying to say is that if you want to use this as something like hash map and you want to look up foo, at each level you can set up B-tree in such a way that I don't know, basically everything that is that you would only need 5, or in this case 3 lookups to know where it is. You will be like, okay, is foo less than is foo in this bucket or in this bucket, is foo in this bucket or in this bucket or in this bucket or in this bucket, and you come to the right choice. Usually what you use here is some kind of comparison, or even you can still use hashing of the input to convert it to something that can be used in a B-tree. So B-trees, they have pretty decent cache stuff. You have pretty decent cost of inserting things because similar to arrays, you just break one. Let me grab something, some other color. You break basically one bond or 2 bonds, and you point to some new memory and restore this stuff. So it's not too bad in terms of complexity for insertion. It is pretty fast for lookups. Maybe not always as fast as hash maps, but pretty close in majority of the cases. Yeah, it has pretty good iteration speed because these things are usually sorted in a way that you want them to be sorted. So going through this all at once is also not too bad. So yeah, in this very incoherent whirlwind tour of data structures, if you want to have some workhorse that you can always rely on and it will be pretty decent at majority of the stuff, you use B-trees. In fact, this is what is used a lot in databases for storage, and just in general, if you want to learn about some data structures that you can apply to majority of problems, look at this stuff. Obviously, look at hash maps, understand trees, think about all of these things, which I'm going to recap just in case. So firstly, understand the relationship between the input and your stuff, understand is your data equally often accessed, and if you how often does it happen in the input. Another like example of this that is very common, especially with compilers, is it is very uncommon in majority of the languages, even the ones that are used in, for example, Asian countries or countries that use Cyrillic alphabet. You still majority of the time you have just ASCII characters as the identifiers and function names. So while you have maybe bigger things that support the whole Unicode 21-bit range, these things are happening way more frequent in a program, and especially something like space, right? So white space happens even more in programs. So while something like a smiley face, right, is not so frequent in programs. So having data structures to look up the ASCII bytes fast while looking up smileys less fast is okay. So this is something you definitely need to pay attention to. Okay, which data is processed together? Again, try to put things that you will go through in iterations in such a way that it is easy to go through in iterations. Like, don't try to shove into a tree or linked list something that you have to process 10,000 times. It's just not going to work out very well. At the same time, you have to be conscious about how you're accessing data. Do you need to do it by index, by some key? How often do you access it? Can you in general store it in an efficient way, but then put some kind of cache in front of it that makes it faster to access frequent things. If you work in a low-level language like C or C++, you definitely need to think about stability of pointers. You need to understand, can I just store this pointer to this there, or from which boundary to which boundary is it okay if I do that? For example, in compilers, you might say that if you have multiple passes over your code that you do, it's okay to store pointers within one pass, but then next pass may just do something else to the memory. In games, you have usually a situation where you're not allowed to store pointers between frames of the game. Like just thinking about that is really important if you are doing low-level stuff. Rust is actually will not allow you to do bad things here, so that's something to think about if you want to do this stuff. So Rust is a good choice there, but it has its own interesting set of problems connected to pointers. And finally, you have mutation patterns. So how do you change this stuff? If you have an array here and you decided that you want to, instead of this argument, you want to insert over here, let's just say you had these and you want to insert over here another 3 elements, then you kind of just asking for trouble, because you have to move all of these stuff by 3 elements, and then it has to be very expensive. So maybe you need to think about something else. But again, if you look at arguments, you usually don't do that, right? So you need to really understand what is your pattern of usage, what are you trying to do, and what are you trying to achieve. Yeah, cool. I think this is all I wanted to say about this. I know it was a bit of a disjointed explanation, but I still feel it's better than not having an explanation at all. And since I mentioned these things here and there throughout the whole series so far, I thought it would be a good time to address at least the very tops of these things. If you have any questions, just leave them in the comments below. I will be happy to answer them and maybe do videos on more specific topics. For now though, I thank you very much for watching, and hopefully see you next time.